come. I think your homework is due, the last homework, I can't remember when it's due, but it's due, is it next Tuesday? A week from today? A week from tomorrow, rather. And when are your project reviews due? They're due at the same time, is that right? Do people, let's look at the schedule. Oops. Did we give a deadline for the project reviews? People remember when that is? Well, it might be on Piazza. I guess I'm not finding it here, but your project review should be pretty soon, due pretty soon, right? Can somebody just make sure that we didn't miss anything? Did you guys get a deadline for that, for the project reviews? You did, okay. So make sure to do those as well. I'm guessing that they're going to be due around the same time as the second homework, but we'll have to check Piazza for that. Those should be very straightforward, right? You should put time into them because you want to make sure you give each other good reviews, but that shouldn't be, a ton of work for you guys. And then after that, you have what we're calling a little test. It's a very kind of short or shorter test in the midterm, and it's going to be completely multiple choice and true-false. So it's just going to be about the level or probably a little bit harder than the quizzes you have. It should be, a very straightforward thing. We're going to try to take questions about the same level or maybe a little harder than the quiz you've had all year and just, compile them into a test that's completely multiple choice and true-false. That'll be the last week of class. So those are your duties, really, right? You have the homework, last homework due, and then this week and next week of lectures, the week after is your little test, and then you're just preparing for your projects. So the end is near. If you guys find this class a lot of work, the light, you can see the light at the end of the tunnel. The end is near. Any questions? Okay, so I wanted to just start off by clarifying something that we talked about with court and dissent. I guess I went through this a little bit quickly, and I got some questions about this particular statement I made. So let's clarify that before we start with today's material. So last time at the start, we gave this simple proof that if you have a function, and that function is a sum of a smooth function plus another function that separates over, say, coordinates, right? So if we had something that looked like this, then we said that if you had a coordinate-wise minimum of this function, so any point that was exactly minimized this function if you try to move along any coordinate direction, then that would imply that you have a global minimizer. Okay, and we gave a simple proof for this, and there's one step that we went a little fast. Looks like we went through it a little fast because people had questions about it, so let's just make sure that's clear. I think it's another example of how being very comfortable with subgradients, say, is a very powerful thing. So what we did is we took f of y. We said, let's suppose x is a coordinate y's minimizer. And we took f of y minus f of x. And, right, it's of course equal to just g of y minus g of x plus the sum of hi yi minus hi xi. And we used the property that g is smooth and convex, right? That we can lower bound this by the gradient of g at x transpose y minus x plus the same thing, right? And then we just wrote this out. Right, I'll just keep this here so you can see what happens. we just wrote this whole thing out as a sum over all I of the ith component of the gradient of g times yi minus xi plus hi yi minus hi xi. Okay, and I claim that this thing, each of these terms, were bigger than or equal to 0. And I guess went through this a little bit fast, and this is what I want to do a little bit more carefully here to show you why this is true. Let's suppose that we really have the property, right, that along any coordinate direction, this function is minimized at x, where we are. So let's use that property for the ith coordinate direction, right? So let's treat this function as just a function of xi. And let's apply subgradient optimality, right? We know that since we're at a coordinate-wise minimizer, in particular, if we treat this as a function of xi, it's minimized at xi over all other values that we could moving along the ith coordinate axis. So that tells us that 0, right, is equal to, or rather we can say that the gradient in the ith direction, so this would be treating this function as just a function of xi, so taking the partial derivative with respect to xi, plus taking the subgradient of this only with respect to xi. You can see the only term that's going to appear is this guy. This has to contain 0. Right? This is subgradient optimality. Applied along the direction, the ith coordinate axis. So hopefully that's clear to everybody. Is there any confusion about that? Just treating this as only a function of xi and saying that it's minimized at xi when I try to take any other value along the ith coordinate direction. So this is just literally the property, like I said, of x being a coordinate-wise minimizer. Okay, so in other words, we know that minus the ith partial derivative of g at x is a subgradient of hi at xi. Okay, well, what does this mean? Let's just use the property of what this means in terms of subgradients. It means that if I have any other point, let's call it yi, and I form a lower bound, a linear lower bound with this term, right, serving as the role kind of as the slope, because it's a valid subgradient, then it means that this is true. Right, that just comes directly from the definition of the subgradient. The property that this is a subgradient of hi at the point xi. And if we rearrange this, we'll see what we exactly get. This term is bigger than or equal to 0. Right? We just move everything to this side, for example, and we just get that the gradient of, or the ith partial derivative of g at x times yi minus xi plus hi yi minus hi xi is bigger than or equal to 0. And that's what we wanted. Okay, so here it's very short proof, like something like maybe 8 lines or something, right? 8 to 10 lines, saying that coordinate-wise minimizer for a function that's smooth plus separable implies a global minimizer. And this could even be, these could be blocks of variables. There's nothing special about coordinates here. If they're blocks of variables, then we'd have to be a little more careful here about taking a block of the gradient or something like that. But it would be the same argument. Any questions? Okay, let's take a vote now, because I'm not actually sure whether we should spend more time on coordinate descent or just move on to the today's topic. I think the two options are we can spend a little more time on coordinate descent. And really, what I would talk about is related to coordinate descent. It would be screening rules. which are often used in the implementation of coordinate descent algorithms, but they're not really directly a core coordinate descent topic. So we could cover screening rules at the end of this lecture, and that would kind of spill into today's topic, and so we could then move on probably, I don't know, halfway through, we can talk about proximal Newton, which is today's, the Frank-Wolfe method, which is today's topic. And then if we did that, we may end up skipping one of the advanced topics, because we probably run out of time. So we might skip something like the exact path following algorithm, for example. That's option one. Option two is that we just leave the screening rules alone, and we go on to Frank-Wolfe, and we talk about that, and then we maybe get to another advanced topic before the end of the class. I actually don't have a preference, so let's just see what the class's interest is. Who wants to stay with screening rules and go through that today? And who wants to move on to proximal Newton? It seems very divided. Let's try that again. Just be a little more, raise your hands higher. Who wants to stay at the screening rules and proximal Newton? It's a toss-up. I keep saying proximal Newton. We're talking about Frank-Wolfe today. Proximal Newton would have been on Thursday. For some reason, I have it in my mind that we would talk about it today. Let's go through the screening rules quickly. There's no real reason not to, and if we move fast enough, we could still get to everything else. So we'll just see how much time we have. It's an interesting topic. It's another topic that's become quite popular as of recently. So at least at every major ML conference, every NIPS, every ICML, etc., I think you'll see at least one paper nowadays on a screening rule. And on your homework, you're doing a screening rule for the support vector machine, which is, I think, pretty neat as well. So this all really started with one paper, as far as I can tell. This paper by El Gaoui, who's at Berkeley in 2010. It's a very interesting concept. Don't know what happened. And they're not directly kind of a core topic in terms of coordinate descent, but they're often used in conjunction with coordinate descent, because they're often used in conjunction with an active set method. And so they're very related. But the kind of brief description is that screening rules describe a set of kind of methods, a set of techniques, which try to, in a very simple manner, so without solving the optimization problem, they try to determine structure at the solution before actually solving it. And so they're kind of applied in two different ways. One way is for sparse problems. Screening rules are applied to try to determine which features will be inactive at the solution without actually solving the problem. So it's a sufficient condition for kind of throwing out some features before you even solve the problem. Another class of screening rules, like the one you're studying on your homework, try to throw out instances. So they actually try to determine kind of, say in a support vector machine context, which observations or which instances will not be support points. So again, you can kind of safely get rid of those before solving the problem. And so they've become a very hot topic, because you can imagine if you can make these decisions, say with a single pass for the data set or with a very simple rule that maybe only takes linear time, then you can really save yourself a lot of computational effort for large problems. We're going to describe the safe rule for the lasso, this was where it all started, really in the lasso context with what these authors called the safe rule. And the rule is as follows. If I'm solving a lasso problem with feature matrix X or predictors X and response or outcome Y, and I want to solve the problem at lambda, then I just go through every inner product that I see. This is the inner product of my ith feature with Y. I look at its absolute value, and I compare it to something. Compare it to this right here. Right? Lambda minus the norm of my feature times the norm of the outcome times this ratio. Lambda max is defined as the largest value of lambda for which all components of the solution are 0. And that's known in closed form for many of these problems. So it's another good exercise kind of involving duality, say, or the KKT conditions. Convince yourself this is true. I claim that if you're solving a lasso problem and you take lambda max to be equal to this value, then the solution will be the all zero vector. So if I take the largest absolute component of x transpose y, the solution to the lasso problem will be the all zero vector. For any smaller value of lambda, that won't be true. You'll get at least one non-zero component. And for any larger value of lambda, of course, you'll still get the all zero vector. So go ahead and try to check that using the KKT conditions or duality. You can do it either way. It's another good practice problem. So that's something we compute ahead of time. Typically, all these algorithms would compute this anyways because they would recognize that any value of lambda larger than this value that the user passes, you don't have to even optimize, right? If the user passes in a value of lambda larger than this, then we can just return 0. So usually this is computed anyways. It takes just a very short calculation to compute. And the rule is as follows. If I take, like I said, the inner product of the ith feature with y and I compare it to this value, then if it ends up being smaller, an absolute value than this value, then I can determine that at the solution, I would have had the ith coefficient equal to 0, the ith component equal to 0. And so I make this one pass at the data set, right? This one sequence of n inner products I take. I compare them to these right-hand sides. This right-hand side is also going to change with I, right? Just because of the norm of the feature here, different. And if it happens to be that I get, the absolute inner product less than this value, I just say that, okay, well, it wouldn't have been a non-zero at the solution anyways. I can discard xi from my data set. So I actually solve a smaller lasso problem. Don't even include that column in the X matrix when I go to solve the lasso problem. Now this is a safe rule because the reason the acronym SAFE was used is because this is a non-random, it's a deterministic inequality. So if this happens, then it is always true that beta hat I is equal to 0. So you can safely discard it. There's nothing random here. It's completely deterministic. There are other rules that aren't safe, that maybe can even do more than this, which say that if something like this passes, then with high probability over the data generating distribution, it is still true that the feature is 0. But it could be in some instances you actually threw it out by accident. So those are not safe rules. Sometimes those are called strong rules because they are able to discard more features than the safe rules are. And I think I gave some references at the end for both of them. But let's study this one. This is actually quite an easy rule to prove from the dual of the lasso. And it's also important to note that this is not an if and only if statement. Okay, if things pass this, doesn't mean that they're going to be non-zero at the solution. That would be amazing, right? If I told you I had a rule that exactly determined which variables were non-zero at the solution for the lasso, that would be amazing. That would almost be too good to be true, right? Because we think of the lasso as performing variable selection in some kind of complex way we can't quite understand. That's the output of an optimization problem. If I told you I had a closed form that determined exactly which variables it was going to choose, that should be very surprising. And that's not true. This is sufficient but not necessary, right? In other words, it could be the case that I run this and I throw out no features at all. I throw out no predictors. But the lasso solution would still have a ton of them being 0. That is a possible outcome of this screening rule. And there have been many advances in screening rules for the lasso for a bunch of different problems. Like I said, there seems like there's almost a paper every time at every one of these major ML conferences. So go ahead and do a literature search if you're interested. This was the first, and arguably the simplest as well. So let's try to figure out why this is true based on the lasso dual. Remember, the lasso dual is this problem. If you give me, I guess we didn't write down the lasso problem, but probably a lot of you guys remember at this point that it looks like this. And the lasso dual is to maximize this criterion. Over all u being the dual variable. Okay, so that's the primal, and this is the dual. And we could rewrite this. Right, I could get rid of this term, and I could turn this. I could get rid of this negative, make this a minimization problem, but ends up being helpful just to keep it like this for now. Okay, So what is the idea behind the safe rule? Well, the idea is as follows. Let's suppose that I was able to find a dual feasible point. Call it U naught. And the better the dual feasible point, the better the rule. So if I could find a feasible point that was very close to optimality, I get a better and better screening rule. If I have a feasible point that's just feasible but far from optimality, I have a looser screening rule. But any feasible point will suffice. Okay, and if we were just starting from scratch, and we never solved a lasso problem with y and x, we could still get ourselves a dual feasible point just by taking u0 to be y times lambda over lambda max. Right? Remember that lambda max was equal to the largest value of x transpose y in absolute value. So it's the infinity norm of x transpose y. You can check that if I take x transpose u naught, this value, right, then I'm getting, and I take the infinity norm of that, then I get the infinity norm of x transpose y over lambda max, which is 1, times lambda. So it's actually equal to lambda. So it's definitely going to be feasible. Okay, so this is just usually called dual scaling. I can just take my response and scale it to make it dual feasible. So that's kind of like the poor man's dual feasible point. There are other ways to get better dual feasible points that may cost more, but we can just stick with that one for now. That'll give us the safe rule we wrote down before. Okay, but if I have a dual feasible point, then g of u0 lower bounds g star, which is going to be the optimal value of the dual problem. Right? Because the dual problem is to maximize this criterion over all feasible points. Certainly a feasible point will give me a lower bound on the maximum. So I can actually, as I wrote in here, right, let's just call this gamma, this value gamma. Then I can go ahead and I can just stick in the constraint that g of u should be bigger than or equal to gamma in my dual problem, and I have not changed the problem. Right? This has not made the problem any different. The solution to this problem is still the solution to my original dual problem, because I know that at the solution this is certainly true. So this constraint is not going to matter at the solution. And now we consider computing the following. We're going to look at every component of xi transpose u, and we're going to try to make that as large as possible in absolute value. Right? With respect to the constraint that g of u has to be bigger than or equal to gamma. And if I am able to solve this subproblem, and I discover that over all points for which g of u is bigger than or equal to gamma, I can make, say, xi transpose u an absolute value only as large as lambda over 2. So mi would be lambda over 2. Then that implies that at the solution, beta I is going to be 0. Why is that? It's because, well, let's think about first just this later implication. From the KKT conditions, right? From the KKT conditions, if xi transpose u is less than lambda, strictly, that implies that beta I is equal to 0. So how do you see that between these two problems? Write down the Lagrangian and different. So remember, to derive the dual, we usually define this to be z. And we put in a constraint that x beta is equal to z. That'll lead to this dual. We've done that in a previous class, I'm sure. Write down the Lagrangian and differentiate the Lagrangian with respect to, I can't remember if it's z or beta. Maybe differentiate with respect to z. You'll see that we have the property that x transpose u is equal to lambda times the subgradient of beta at the solution. Okay, so if it's strictly less than lambda, means the subgradient is strictly less than 1, that implies that the solution has to be 0 on the ith component. This implication I'm pretty sure we've done before in class as well. So this should ring a bell. But if this doesn't ring a bell, It's easily derivable from the primal dual relationship. So essentially we're seeking the dual points, or the coordinates of the features, such that when I take the inner product of that feature with the optimal dual value u hat, it's strictly less than lambda. That would tell us that we don't have to consider those features at the solution. And what this is doing is that it's giving us a sufficient condition for this to be true. Right? Because if I'm able to maximize xi transpose u over all u for which d of u is bigger than or equal to gamma, and make that, say only lambda over 2, then certainly at the solution, I also have to have xi transpose u hat is less than lambda. Because look, this maximization problem, it has less constraints, right, than I have in my dual problem. I'm only forcing that xi transpose u has to be, I'm only enforcing that g of u has to be bigger than or equal to gamma. And I'm trying to look at the largest possible value of xi transpose u. This value m, this maximum could occur when, say, xj transpose u was twice lambda. There's nothing stopping that here. Right? So in a sense, I'm looking at a larger constraint set than I have here. So if the maximum over a larger constraint set is still less than lambda, it's going to be true over the smaller constraint set too, which is what we're looking at for the dual problem. Okay? Stare at that for a second because it may take a second to interpret. Now you can see why the dual lower bound is so important, right? If I didn't have this, then this doesn't make any sense, right? The largest I can make xi transpose u is infinity in absolute value if I don't have any constraints. And if I try to, another thing you might think to do is, well, let's just maximize xi transpose u subject to all the other ones, right? xj transpose u is less than or equal to lambda in absolute value for all j not equal to I. Well, that would also give you a valid screening rule, but that's just too hard. The trick is to make the subproblem easy enough that we can solve. So we're going to want to actually compute mi in closed form. So easy enough that we can solve, but hard enough that it actually gives us some leverage. Right? It has to be that this lower bound, this quantity mi is not trivial in some sense. It has to actually still retain some information about the problem. So that's why this is kind of a cleverly constructed rule. Here's the picture. Some people find this picture very clear. Some people find it very confusing. So, I don't know whether or not I can explain it much better than this. But you'll have to stare at it for a while if it doesn't make sense. So this is supposed to be showing the dual constraint set. It's x transpose u, and infinity norm less than or equal to lambda. Right? It's a convex polyhedron because it's the intersection of a bunch of half planes, half spaces. xi transpose u, say less than lambda, and xi transpose u bigger than minus lambda for each I. And what we're doing is we suppose that this was our theta is the dual variable here. So suppose that we actually, through dual scaling, we obtained a feasible point here, theta. Okay, and let's suppose that this gives the contour of the dual function at optimality. So when we look at theta star, and we look at the contour of the dual function, we know it's going to touch the constraint set. Right? That should be kind of intuitive in a sense. What we're actually doing is looking at a lower contour of the dual function. Right? So if you think about this in 3D, this is a hill with the highest point of the hill here, and the hill kind of descends in all directions. And this is a slice of the hill at some value, and this is a slice of the hill at some lower value. And we're actually going to add this constraint to our dual problem. Right? It doesn't change the problem because the solution is going to lie kind of on a higher point on that hill. And now we go ahead and we look at every face of the polyhedron, or really every half space that determines the polyhedron. And we ask the question, if I look at the largest possible value, so each one of these has a normal. Let's look at this guy right here. Look at the normal vector to this. The normal vector to this is going to be determining the value, say, of xi transpose u, or some u. And these are the values for which it's equal to lambda. If I restrict myself to lie inside this purple contour, and I try to make that value as large as possible. You see I do that right here. And here I have xi transpose u strictly smaller than lambda. So I haven't reached this hyperplane here, which is xi transpose u equal to lambda. So we know that at the solution, therefore, this can't be active also. Right? At this inner contour, which represents the solution, we still can't have xi transpose u being equal to lambda. So this is not going to be active at the solution. So we've safely ruled out this constraint and this constraint, 2 in green. There are a bunch of other ones which at the solution are actually 0 as well. So it's these 3 red constraints, because the solution only touches this face. So we have not ruled those out. So the safe rule is sufficient but not necessary. But at least we rule out these 2 constraints. Kind of a geometric picture of the safe rule. Okay, and this geometry ends up being useful. Most of the subsequent work that's being done on screening rules is all based on convex geometry. So we're going to just quickly sketch out how you compute this value, mi. And you'll see that if I compute this value and I write down the rule mi less than lambda, that exactly gives me the rule that I had before on the previous slide. And so that'll give you the safe rule then. Okay, so we want to compute, say, the maximum of xi transpose u subject to g of u being bigger than or equal to gamma. And also we want to compute, we want to solve this problem, but for minus xi transpose u, minimize minus xi transpose u. Minimize xi transpose u. Right, we want to compute the max and the min. If we compute those 2, it'll give us the biggest and absolute value that xi transpose u can be subject to this constraint, g of u bigger than or equal to gamma. Another dual argument, so another good thing to practice is take the dual of this problem. How many variables should that dual, how many dimensions should that dual problem have? It should have just 1, right? Because there's only 1 constraint. So the dual problem is going to be univariate, even though this problem was an Rn. And the dual variable here I'm calling mu. And the dual ends up looking as follows. Minimize overall mu bigger than 0 minus gamma times mu plus 1 over mu times the norm of mu y minus xi squared. Okay, so this, the dual of this is this problem. And from strong duality, we know that their optimal values will be equal. So kind of a second application of duality. This one is actually quite easy to solve because it's univariate. So I can just differentiate this one and set it equal to 0, find the optimal value of mu and plug it back in. That's all I've done here. So I'm just leaving out some details because they're not interesting. But you can work that out if you're curious. So the optimal value of this problem is equal to the optimal value of this one, and it's easily computed because it's univariate. And it ends up just being the norm of xi times the square root of the norm of y squared minus 2 gamma minus xi transpose y. This comes from the direct calculation. And mi, right, it's the maximum of this over plus or minus xi. Because mi is equal to either the maximum of this problem or the minimum of this problem. I could think about it as the maximum of this problem or the maximum of the problem where I put in minus xi there. So if you think about maximizing this quantity over plus or minus xi, you'll realize that actually all I have to do is put an absolute value of xi transpose y here. This will always be positive. It won't change with plus or minus xi. This part, right, it's going to be negative for one of minus xi and positive for the other. And so when I maximize, I'm going to, of course, take the one that's positive. So this is the maximum over plus or minus xi of this quantity. So this is mi. And now we know that if I actually just compare mi to lambda, if this is less than lambda, then I have a safe rule. Whenever this is less than lambda, I can safely discard feature I. Just don't even load it into memory if I have a big problem when I go to solve the lasso problem. And just rearranging that gives you the rule on the previous slide. And I've just plugged in gamma for the, this is the dual criterion at our dual feasible point. Okay, so just a simple rearranging gives you this rule. Which is kind of an interesting rule also from a statistical perspective, because we can think about let's think about all of the variables xi having unit norm, right? Which is something that's actually not that uncommon to do for the lasso anyways, because if we're going to be penalizing the absolute value of the coefficients, if the variables are on a different scale, it doesn't make much sense. So sometimes, as a common pre-processing step, people normalize the variables anyways. So that means that this right-hand side is just a single number. It's lambda minus the norm of y times the ratio of lambda max minus lambda over lambda max. And another common thing to do is to center the variables, right? If I wanted to include an intercept in the regression. So in that case, this would really be the correlation between xi and y. We're looking at the correlation between xi and y. And this is a threshold. It's saying if the correlation does not cross some global threshold, the same for all I, then I know the lasso won't choose that variable, so I don't have to include it in the actual optimization problem. It's interesting because we don't think about lasso and correlation screening on the same footing, right? Correlation screening is so naive. Something that people did for years and years and years before kind of fancy high-dimensional regression procedures. But this is a sufficient condition for the lasso to throw out a variable. So it's a pretty interesting kind of relationship. One other thing I'll say is that to make the safe rule very effective, so you can take a look at this paper, this one I mentioned here and some of the other papers at the end, you can see that if you're very far down the path, if I'm trying to screen out variables when lambda is far away from lambda max, this gets less and less efficient. The proportion of features screened away gets smaller and smaller. Okay, because you can think about the dual feasible point that we're using is farther and farther from optimality. Right in this picture, if I take whatever y was and I scale it down just to be dual feasible, if lambda is really small, the dual feasible point is kind of weaker and weaker, this guy here. So this lower bound is looser and looser on the optimal dual problem. And so the rule is less and less effective. So what's commonly done is that the lasso is solved over a grid of lambda values, and the dual feasible point comes from the last solution. So that's the last solution admits a dual optimal point, and we scale that down to get a dual feasible point for the smaller value of lambda. And that actually gives the tighter lower bound. And so that's sometimes called sequential safe screening. And that can be pretty effective. So what's commonly done in, say, the state-of-the-art coordinate descent algorithms is that they start off by screening out variables. They just throw out a bunch of variables. And then among those variables, they do a single coordinate descent pass number, and they actually get an active set that's just the one that survived that first thresholding pass. And they iterate over that until convergence, and they check the KKT conditions. So what they're really optimizing over is a much smaller set of features than the full set, because it goes through two screening rules. One, that's this screening. The second, that's the first loop of the coordinate descent algorithm. And then to move on to the next value of lambda, they do the same thing. They screen away using this screening rule, maybe with a smarter value of the dual feasible point. They do a single pass to get the active set, and they iterate over a very small active set until convergence. So for this reason, it's oftentimes true that solving a very large-scale lasso problem can actually be more efficient than solving a large-scale ridge regression problem, which might sound bizarre, right? Ridge regression is smooth. It actually has a closed-form solution. It's a solution to a linear system. But at really large scale, we actually have better luck solving lasso problems, when done, say, with coordinate descent than we do a ridge regression problem, which is, I think, kind of surprising. All right. Is there any questions about screening rules before we conclude? Yeah, I don't think there's some references there at the end you can take a look at. Okay, so for those of you who wanted to hear about screening rules, hopefully now you can go write a new paper on them. For those of you who didn't want to hear about them, I'm sorry, but that was that. And let's take a 5-minute break, and then we'll come back and do Frank Wolfe. Talk about conditional gradient method, also called the Frank Wolfe method. There's kind of a theme you can tell with these last set of topics. They're things that are very popular right now. So I've said that a lot. As I see it, and this is probably not a very historically accurate, representation, but coordinate descent was very popular, say in 2009, 2010. It still is, but that was, at the time when everyone was really working on it really hard, and it had a comeback in some sense. Then came these methods, conditional gradient and Frank Wolfe, 2011, 2012. And these were very, very popular at a time. And then now, and maybe even I'd say 2011, 2012, 2013, now it seems to be fast stochastic methods that are gaining a lot of popularity. This is all within the ML optimization community. I'm speaking on behalf of, from what I can tell. But I don't think that's very accurate, and it's not. I didn't document this anyway, but this is just my impression. These are still all very popular. People are still really intentionally pursuing these methods, but they each had kind of a wave in some sense. So what does the conditional gradient method look at? So we go back to a constrained optimization problem where we're minimizing some convex smooth function subject to a constraint set C, x being in C, where C is convex. So we have different methods for solving this, right? But in the context of first-order methods, we really have one, which is projected gradient descent. There are some variants we could do, but projected gradient descent is kind of like our staple. Right, so what we do is we take a gradient step with respect to f, and then we project onto the constraint set. Repeat that over and over again. And that was a special case of proximal gradient descent. Remember, we saw that this is actually the same as just having moving this into the criterion as an indicator function, writing that as h. And this was actually just applying the proximal operator of that function h, say. But you can think about it like projected gradient descent nonetheless. It's natural on its own. How do we motivate that? Well, the way we motivated proximal gradient descent was actually, in gradient descent in general, was actually to take a quadratic approximation of this function and to minimize that quadratic approximation and then project back onto the constraint set. That's what we're doing. So at every step, right, we're forming this function. I left out the constant term, but we take f and we represent it by this quadratic function. Let's call it f hat quad, quadratic approximation to x. Let's think of it as a function of y. And if we're at the step k, so we're looking at forming a quadratic approximation about xk minus 1, then it's done as follows, right? We take essentially the first two terms in its Taylor expansion. And we add a quadratic term that looks like this. Say tk. So you can think about that like I'm taking the Hessian here to be just a multiple of the identity. It's actually 1 over tk times identity. That's this quadratic approximation. Right? And what kind of validated, in some sense, gradient descent was that if we chose tk appropriately, if it's equal to 1 over the Lipschitz constant, for example, of the function, then we know this quadratic approximation actually upper bounds our function. Right? That's another property of a function of a convex function with a Lipschitz gradient. And so by minimizing this quadratic approximation, we're minimizing the upper bound of the function, and you can think about it like we're minimizing a majorization, and so we're getting closer and closer to the minimum. So what we do in projected gradient descent is very similar. We form this quadratic approximation. If you were to minimize this, you'd see the minimizer is exactly this gradient step. And then we just project back onto the constraint set over and over again. Projected gradient descent, just as a refresher. I'm sure that you guys all know that by heart at this point. So what does Frank Wolfe do, or the conditional gradient method? They're used synonymously. It does something different. It actually, instead of taking this quadratic approximation, it takes a linear approximation of the function. So it doesn't have a third term at all. This uses this. Now, what happens if I were to minimize this and then project onto the constraint set? What would that do? Minimize this overall y. happens if I minimize a linear function? This is just linear in y, right? Look, there's only one appearance of y. It's not a trick question. It's supposed to just be, yeah, you don't get, you're right. Sends off to negative infinity. You don't have something to project onto the constraint set. Right? So if I didn't have constraints, first of all, this would make no sense. I can't take a local linear approximation and then minimize it. Right? That would just, if that was my function, that would just send me to minus infinity. And I can't take a local linear approximation and then project on the constraint set for the same reason. Right? It's not well defined. So what Frank Wolfe does is actually minimizes this over the constraint set. So Frank Wolfe is going to minimize this over the constraint set. We'll take, I think I called it S on the slide. S k minus 1 is the argmin over all y in the set C of f hat ln y. Okay, so you might think that actually it's a good idea just to repeatedly do this over and over again, which is a bit synonymous to what happens in gradient descent, except for gradient descent replaces this by the quadratic approximation, f hat ln by f hat quad, and instead of minimizing that over the constraint set, it actually performs those separately, minimizes the quadratic and then projects onto the constraint set, just because that's easier to do. It's easier to do that computationally. In Frank Wolfe, we changed the approximation, right? We changed the nature of the role of the constraint set. But we also just don't repeat this. We don't call this xk. We actually have to be a bit more careful because we're doing something actually very different from minimizing a quadratic approximation. And so what we do is we look at this minimizer, and then we just move a bit in the direction of that minimizer. So we call our next iterate, say xk minus 1 plus gamma, say gamma k, times sk minus 1 minus xk minus 1. Right, so if I were to draw a picture, which I can't really draw a great picture of, this is our constraint set. Actually, there's a better picture, I think, on the slides coming next. So you have to settle for that if this is not a very telling picture. But suppose I'm here, and I minimize, and my function, this is my constraint set, my function lies somewhere above this, and I form a linear approximation to it. And that linear approximation tells me to go all the way to this boundary point of the constraint set. So instead of taking this to be xk minus 1, and then jumping here to be xk, I actually just label this sk minus 1, right, and look at this direction. This direction is sk minus 1 minus xk minus 1, and I move a bit along this direction. So I start at xk minus 1, and I add gamma times this direction, and that might give me xk. And so we're not kind of being quite as aggressive as just taking the minimizer each time. And this gamma is a step size. Gamma k is a step size. I can also write the update like this, right? I can write it as 1 minus gamma k times xk minus 1 plus gamma k times sk minus 1. So you can think about it like I'm taking a convex combination of these 2 points, and it's having me end up here. Another way to think about it. And these gamma k, like I said, are a step size. The default choice is to choose 2 over k plus 1. So another difference to, say, projected gradient descent is that we actually, maybe the most common is to use step sizes of this form. We can also do something like line search, but we'll talk about that later. We typically, the default is to take a fixed step size like this. Okay, so as the step size gets smaller and smaller, right? As the iterations go on the step sizes get smaller and smaller. This is getting closer and closer to 0. You can see I'm being less and less aggressive. So I'm actually moving less and less along the direction of the minimizer. So I take very big jumps at the start, and in fact, when k is 1, this thing is gamma is 1. So I just go from the first iterate goes from my initial point to whatever the minimizer is, and it jumps around a lot at the start, and then we kind of slow down and we just follow the direction of the linearized minimizer less and less. I think it's a pretty intuitive method on its own. We're going to see it has a lot of nice properties. Yeah, Justin. Because it makes the proof simple. There's not really a special choice of 2 over k plus 1. Just makes the proof simple. I don't know if you recall, we had a lecture on it. Well, we didn't really talk about it in too much detail, but in the accelerated gradient descent lecture, we had a choice of a kind of acceleration weights, the momentum weights. And they looked something that was equally, kind of arbitrary. And that was, again, just to make the proof simpler. We're going to see, and I don't know if I included the proof. I included part of the proof. We're going to see that this has the same convergence rate as projected gradient descent. Other questions? Okay, the reason this is called the Frank-Wolfe algorithm is because in 1956, Frank and Wolfe wrote a paper called, I think it was called something like an algorithm for quadratic programming, or local linear algorithm for quadratic programming. And they proposed this algorithm just for quadratic programs. And we'll see the motivation for this. Essentially, the updates can be very cheap here, much cheaper than projection to a constraint set. So it's a very efficient method in terms of the costliness of its iterations. And I actually don't know, maybe Javier can tell us, I don't know about a ton of work that was done on this since then. I don't think. Not much, yeah. I think it was clear from that paper that it could be done beyond quadratic programs as well. It's just that it's another one of those things where it was kind of revisited recently in the ML community. This is sometimes called the linear minimization oracle, by the way. If we take a linear expansion of our function, we minimize it over the constraint set. Linear minimization oracle. So this is a picture that I took from this paper by Martin. I'm going to say Jaggi. It might be Yagi, since I think he's Swiss. But this is a very nice paper he wrote. It's actually his PhD thesis was on Frank-Wolfe methods. So he was a PhD student and was very interested in Frank-Wolfe methods, and he kind of brought some attention to them back in the ML community. So this is trying to explain this same concept I was drawing, which is that this is our function. We take a linear approximation to our function. His constraint set he called D, and the minimizer might be S, and we move in some along the direction given between S and X by some amount. And a lot of the results we're going to be talking about come from his PhD thesis, actually. He has very simple analysis of Frank-Wolfe in his PhD thesis. So one of the main motivations for Frank-Wolfe comes from norm constraints. Right, what happens if we're trying to minimize over a norm constraint? Any norm, the set of all x for which the norm with respect to, say, the L1 norm, trace norm, whatever your favorite norm is less than or equal to t. And this t would be like one of our tuning parameters if we had a kind of common statistics or machine learning problem. Then you can see that the update here actually has a very simple form. We're just going to minimize, right, over all s, the gradient of our function at the current point transpose s. So this is just a linear function. This is a constant with respect to the minimization, the gradient, over all s that have norm less than or equal to t. So let's notice one thing first, which is that the difficulty of this update, right, being able to solve for this minimizer, has nothing to do with f. Has everything to do with the constraint set, or in this case, the norm. Right, because with respect to this minimization, the gradient of f is a constant. We're just evaluating at our current iterate. So it's like proximal gradient descent methods, where the prox operator has nothing to do, the difficulty of the prox operator has nothing to do with the smooth part, entirely to do with the non-smooth part. So as long as we can compute gradients, the difficulty of these iterates is the same. It's unchanged. For norms, we can say something more, which is we can actually get kind of a more explicit form for what this update is going to look like. And that's pretty simple. Let's just, first of all, let's just call, let's replace s by t times s. And so we're going to look at all points s that have norm less than or equal to 1. This comes from the positive homogeneity property of norms. Right, that I can always just pull out a constant with the norm. And you can see that if we do that, we get t times the argument over all points for which s is less than or equal to 1. Now I'm just going to switch the argument to an argmax, and I'm going to pull out a minus sign. So the value of s that minimizes this, that maximizes the inner product between the gradient and s over all values s that have norm less than or equal to 1. If I multiply that by minus t, it's going to give me the argument of this problem. Just two kind of very simple steps there. What is this inside guy? Should look familiar from our lecture on subgradients and things we've done since then. Well, first of all, the maximum over all points s for which s is less than or equal to 1, let's say of A transpose s, that's by definition the dual norm evaluated at A. It's the definition of the dual norm. And so the argmax here is an element of the subgradient of the dual norm. Right? We learned that subgradients of things that are a maximum, pointwise maximum of functions, there was a rule for that. And one of the very simple things you can remember from that rule is that whatever achieves the argmax at A is a valid subgradient for the function. So in this case, whatever achieves the argmax is a valid subgradient for the dual norm at A. So we can replace this. And in fact, for norms, this is an equality. The argmax is exactly the set of subgradients for which they achieve the maximum. And so what we've seen is that s is equal to minus t times a subgradient of our dual norm evaluated at the gradient loss function. Okay, so what do we need to compute this? We need to just know what subgradients of the dual norm are. If you have your favorite norm, you want to perform, you want to use it to regularize your function f, then in order to optimize it with Frank-Wolfe, all you need to know is how to compute gradients of f. That's what goes inside here, and it's treated as a constant after that point, once you evaluate at xk minus 1. And you need to know how to compute subgradients of the dual norm. If you know those two things, then you have a recipe for computing the update s, and then you just feed it back into the usual update rule here, right? You take that s and you move along it by some amount. So the key to Frank-Wolfe is that this is often simpler or cheaper than projection onto this constraint set. We'll see for a lot of problems of interest, computing a subgradient of the dual norm is often simpler, either conceptually, like you can just do it for more cases, or it's actually cheaper computationally than a projection step. So I think either the subtitle or maybe a chapter to Martin Jagi's thesis or a paper he wrote on it subsequently was called Projection-Free Optimization, right? Because it's the idea you don't have to do any projections if you're going to use Frank-Wolfe. Even though you have a constraint set, it reduces to something like this. So we'll get through some of this today. I don't know how much, and we'll continue with it on Wednesday rather. Let's get concrete so you can see what this looks like for certain cases. Let's turn to the case of the L1 norm, right, which is obviously a quantity of interest for regularization. This would give us some kind of sparsity property if we regularize f according to the L1 norm. Well, according to that last slide, all we need to do in order to compute the Frank-Wolfe updates is look at its dual norm, which is the infinity norm. Right? The dual of the L1 norm is the infinity norm. And forget about the gradient at this point. All we need to do is be able to compute subgradients. For the L1 norm, it reduces to computing subgradients of the infinity norm. If we can do that, we can use Frank-Wolfe for this constraint optimization problem. So what are the subgradients of the L infinity norm? Should be something that you haven't forgotten, hopefully. The L infinity norm, right, it's the maximum over all I of AI. Just write like this, maximum A1 through, say, AN. Did I call it P here? I don't know, I called it P for some reason. The dimension I called P. Subgradients of that. What is a subgradient of that? I don't care about the whole subdifferential, just a subgradient for that. I gave you a vector A. We just talked about this a couple of slides ago, right? If I have a maximum and I asked you for the subgradient, you can take a subgradient of the term that achieves the max. So let's suppose that, Aij, or Ai, is equal to the max. It achieved the max. Then if I just take the sign of Ai, that serves as the sign of Ai, and I multiply this by Ei. So I take the vector that has, whatever, plus or minus 1 in the ith component and 0 everywhere else. That serves as a valid subgradient of the infinity norm. Right? Because if I take the subgradient of this with respect to all of A, then it's just going to be 0 in all components except for the ith one and the ith one. If Ai was away from 0, it'll be its sign. And if Ai happened to be equal to 0, this is still a valid subgradient, so it doesn't matter. Okay, so this is I can always, for the infinity norm, I can always just look at which component achieves the maximum and then take its sign and then put all other components equal to 0. That's a valid subgradient. So it's a very natural rule here. I need the subgradient, right, of the infinity norm of my gradient vector, gradient of the loss function, evaluated at my current iterate. So I look at the biggest component of this gradient vector. So look at the biggest partial derivative with respect to all the variables, 1 through p, in absolute value. I call that ik minus 1. So it's the guy that achieves this maximum. And this is now a subgradient, right? Sine of whatever that component happened to be, the gradient times eik minus 1. That's a valid subgradient of with respect to the L infinity norm evaluated at this gradient. And I have to multiply that by minus t, right? That was the update rule. Take that and multiply it by minus t. And then Frank Wolfe wraps it up like this. We take that minimizer and we take a convex combination of that and where we were before. So you can see it's very much like greedy coordinate descent. That's kind of an interesting relationship there. All I do is I think about taking any of the p coordinate steps, right? If I'm just doing a true descent method where I'm descending along the gradient, and look at which one would take me the farthest. That's all this is saying. Which coordinate update would take me the farthest? I choose that one, and I move in that direction. And you can think about it in a couple ways, right? Like I'm taking a convex combination of where I am in that direction, or I just move in that direction by an amount gamma k. So this was a very simple algorithm, right? There's nothing computationally sophisticated here. All it is scanning through and taking maximums of things, and I'm updating just one coordinate of my, only one coordinate of the x variable is being updated at every iteration. Nothing else is being updated. And so it's a lot simpler than projection onto the L1 ball, right? What would projected gradient descent do? It would take x minus the gradient and it would project onto the L1 ball at every step. Projection onto the L1 ball of radius, say, t, that's actually not trivial at all. So kind of the most simple implementations of that, they can be written out in, I'd say, semi-closed form, and they take n log n operations. And if we do it kind of cleverly, we can do it in linear time. But this is like research level. It's a research level topic, right? People write papers about projecting onto the L1 ball efficiently. So you could look that up, and there would be a fast linear time algorithm you could implement. But at least this is a lot simpler, right, than projecting onto the L1 ball. Let's look at LP regularization now. So let's just think about, I want to regularize with respect to the LP norm, or I want to put an LP norm constraint, LP less than or equal to t of x. And p is anything that makes this norm convex. It's between 1 and infinity. Then in order to compute the Frank-Wolfe update, I need to be able to compute subgradients of the LQ norm, where q is the kind of dual or conjugate of p. So I have 1 over p plus 1 over q is equal to 1, right? Because we know that if this is true, then this is the LQ norm is the dual of the LP norm. So I claim that you can actually choose the subgradient. You can actually choose a particular subgradient. It's very easy to compute. And that's something you guys can check if you're curious to see where this comes from. Write out, so where does this come from? Write out this problem. Maximum overall SQ less than or equal to 1 of, say, A transpose S. Write out this as the maximum overall points for which Si to the Q is less than or equal to 1. A transpose S. Now, usually the LQ norm, right, it takes this to the power of 1 over Q. But in this case, I can actually just raise both sides to the Q, and the constraint set wouldn't change. So because of this kind of simple property, I claim you can actually compute the argmax here quite easily, and that it ends up just looking like this. It's a little calculation you can do. So there we go. We take components of our gradient, we raise it to some power, which is p over q happens to be, look at the sign of the gradient, and multiply it by some constant alpha. That alpha, all it's going to do is it's going to make it so that at the end of the day, the LQ norm of our update is actually t, or actually 1, depending on how you wrote it. So it's just going to give it the right, it's going to be a normalizing constant to give it the right norm with respect to the Q norm. Once you have this, the Frank-Wolfe updates are the same. Just take your current iterate and then add some multiple gamma along the direction between this and where you were, or some convex combination of this and your current iterate. Think about it in both ways. This is a case where it's much, much simpler to do this than projecting onto the LP ball for a general P. So I don't know of algorithms that project onto the LP ball directly besides the special cases 1, 2, and infinity. I could be wrong. Do you know of? I don't think that that's something that's known in general. Right? So in order to project onto the LP ball, you'd have to actually run some kind of inner optimization procedure and do it approximately. There's not really much more difficulty here than there is in the L1 norm case. It's a very simple update still. So a big win for Frank-Wolfe. Let me tell you one more example, and then we'll call it a day, and we'll come back. Next time we'll see the convergence properties of Frank-Wolfe. And the last one is trace norm regularization. And this is the one I think where Frank-Wolfe has one of the biggest advantages compared to projected gradient. So let's suppose that I'm looking at the trace norm ball. The setup. So now my optimization variable is a matrix X, and I'm looking at all the matrices X that have trace norm less than or equal to t. Remember, trace is the sum of the singular values of X. So we define this norm. And from an earlier homework, I think, or even lectures, we know that the dual of the trace norm is the operator norm, this guy. So it's the largest singular value. And what we need to know is how to compute subgradients of the operator norm. And we're going to evaluate that at the gradient, right? So again, it doesn't matter what this is. Just think about computing subgradients of the operator norm for a matrix A. See if you can figure out how to do that. Do we have that as homework? I can't remember. Is this a homework problem? It was? Oh, it was in our lecture. I see. Okay, so I guess I already had this in the lecture earlier. Your homework might have been computing subgradients of the trace norm. That maybe was your homework. But in any case, if we take u and v to be the top, left, and right singular vectors of A, then this is a valid subgradient of the operator norm. And if they're unique, actually, if there's no tie for the top singular value, then this is the only subgradient, so that the operator norm is differentiable. This is its gradient. So this is where u and v are the top, left, and right singular vectors. So if I take its SVD, this is the first column of u, and this is going to be the first column of v, or the first row of v, depending on how you're writing it. So Frank Wolfe just needs this, multiplies this by minus t, and it adds that to your some convex combination of that to your current iterate. Right? You look at the gradient of your loss function at the current iterate. You compute the top, left, and right singular vectors, and then you add that rank 1 matrix, some convex combination of it, to your current guess, xk minus 1. So that might seem expensive, right? I have to actually compute the top, left, and right singular vectors. But compared to projecting onto the trace norm ball, this is much, much, much more efficient. To project onto the trace norm ball, I need to actually compute an SVD. This is just computing one term of the SVD, right? The top, left, and right singular vectors. There's a very big difference between those two in terms of computation cost. So I'm not sure whether you would have seen this in another class, but for example, you can use the power method to compute the top, left, and right singular vectors. I use the power method, I iterate until convergence, and there's lots of kind of variants of that as well. So I can do this for very large matrices, A. And I can also take advantage of the sparsity of A with something like the power method as well, because all it involves is matrix multiplication by A, or A transpose. So some people are starting to think about these types of methods for very large-scale trace regularization problems, like matrix completion problems. Think about what we talked about for back when we did proximal gradient descent. We actually looked at the version of this problem that was penalized. Right? I took smooth function plus lambda times the trace norm of x. In some sense, right, it's an equivalent problem statistically to this one, depending on lambda and t. So even the proximal operator of the trace norm is way more expensive than this. It also requires an SVD. Each iteration here just requires the computation of one really pair of singular vectors. So there's a very big difference in the computational cost. Let's wrap. That's it for the day. Let's just return next time to Frank Wolfe, and we'll get to see some convergence analysis then.